The next thing I want to do on my single board Z80 computer project is cost out the Z80's oscillator and the serial chip because these are expensive and these aren't made anymore. The idea is to use the Atmel chip as the serial interface. Now it was acting as a serial interface before, but it was taking RS-232 logic level serial from this chip and then turning it into a USB signal from my computer with a very dirty fan cover. But since we already have the data port of the Arduino hooked up to the data port of the Z80, we should just be able to pass data to the Atmel itself, just like we were passing data from here to here before. So we need to do a few things to make that happen. The first thing we need to think about is the timing of the Z80 and its peripherals.
Microcontrollers have all sorts of timers and output ports you can use, and this is no different. So you may be familiar with the analog write function in Arduino. It basically creates a square wave that simulates an analog output signal on one of the pins. So in the simplest form, we could run this and we should get a square wave on pin 13.
So we've got the Arduino hooked up to the scope, pin 13, and there you go. It's pretty slow, but it works. But obviously this is way too slow for our processor. What to do?
The answer is to RTFM, and I can't say what that stands for because I'm not part of a multi-channel network that can whitelist me to swear on YouTube. 10-bit high-speed timer counter 4. This is what the Arduino framework is using for that pin 13. Get a pretty fast clock through this. We want to look for, what's that called? The PLL frequency. Phase lock loop. Okay, where's the register? There we go. There we go. All right, so a phase lock loop is something in a chip where they take a lower frequency and they multiply it into a higher one. In the case of the Arduino Leonardo, it's taking a 16 megahertz clock and it's bumping it up to 96 megahertz, and then it's dividing that by 2 to get the frequency it needs to run a USB device. The thing that we're interested in is we're interested in the PLL pulse scaler for high-speed timer, right? So this allows us to connect timer 4 to this high-frequency device, right? So these are the 2 bits we're looking for. We can either divide it by nothing, which means it's disconnected, which I assume that's the state it's in now. We can divide by 1, 1.5, or 2. I think we'll do 2, so we will basically be taking 96 megahertz, dividing it by 2, and taking that 48 megahertz clock and feeding it into our timer. Let's go back into our clock example. Now there's probably some other stuff going on under the hood with analog write. We'll just let that happen because it'll speed this along. So we're going to put this into PLL frequency. So basically we're taking what was there and we're adding those 2 bits, which will source timer 4 with this phase lock loop frequency. This is the next register of note, timer counter 4 control register A. Some of this will have already been set by that analog write function. We just want to make sure everything is what we need. This bit means it's going to override the function of OC4A pin, which is pin or digital 13 on Arduino. Okay, clear on compare match, which means it's going to count up to a certain number, and then when it reaches it, it's going to clear the bit. So right now this is set to 0, 1. In these bits. So if you come down here, that means it's clear on compare match. So it's going to count up to a certain amount. So it's going to start as a 1. It's going to count up to a certain amount of ticks, then change to a 0, then count a certain amount of more ticks, and then start all over again. That's how you could create a PWM signal of variable length. Okay, and then also it has the PWM4A bit set. Let's see what that does. PWM4A. Oh, okay. When set, this bit enables PWM mode based on comparator orca like a whale. OCR4A, which again is just that pin. Also, this register is also important. Timer 4 register B. All right. So what do we need on this? Inversion mode, prescaler reset. One thing I really care about is the here we go. Prescaling. So prescaling is where it takes the input clock and it changes it again. Usually it divides it, or pretty much almost always it divides it, right? Right. So these 4 bits basically select a division factor. So like if you selected 1, just 1 bit. It's just going to take that clock as is. So it's going to source this with a 48 hertz clock. Let's see what that looks like. Okay, I made those changes to the code. Let's send that over. So really what we're doing here is we're removing all of the math and scaling that the Arduino function was doing and just doing it manually ourselves.
Everything else is the same as before, but as you can see, the frequency has increased a pretty good amount. So we're definitely making a change. Let's keep going.
What else could we change? Well, we could change all sorts of things. In fact, this timer has far more options than I'll ever use. All right, so we're going to use compare register A and compare register B, right? So basically what's going to happen is there's a timer, right, or a counter, and it's going to count up from 0, right? And when it starts at 0, it's going to be 1. When it hits the value of register A, it switches over to a 0. And then when it hits the value of register B, it resets itself back to 0 again. So if you set this to like 7 and 10, you'd have a 70% duty cycle PWM signal. What I want to do is actually just look at these registers, right? So you can just do this. You can just copy that, and I can go serial, print line, just that register, binary. Well, actually, that doesn't really need to be binary because it's not a bitwise register. It's just a number. I believe you can also bump this up to a 10-bit timer if you want. I don't think we need that much precision. There's a C register too. Oh, there's also, there's a D, a C, all sorts of stuff. Let's just look at all of them. Remember, 90% of programming is copying. Now we have to be careful because obviously we don't want to put a 48 megahertz signal into our Z80 because that would be bad. Imagine every molecule in your body exploding at the speed of light. Oh, okay, yeah, well, here, I'll just turn off the scrolling. So if you remember, we had the analog write 128 out of 255. So there you go. So 128 to 255. So that's basically how it works. So it counts up 128 clocks high, and then it counts to 255 while low, and then it starts all over again. So that would be a 50% duty cycle. So what we can do is if we lower the value of these registers, it will basically, well, it won't count faster, it just won't count as high, which means the clock pulses will be tighter. Okay, so OC R4A equals 1. OCR for C equals 2.
Whoa, look how fast it is now. It's gone up quite a bit. It's way faster than it was. But you know what? We can make it faster yet. Because 94 kilohertz, come on. That's slow. That's like Commodore 64 slow. Shots fired.
So in the 7.3 megahertz Z80 example, it definitely gets a little warm. Or as I like to say, it's certainly semiconducting. So what we can do is we can actually adjust these values and slow down the waveform a little bit. I'm thinking 6 megahertz would be pretty cool.
Ah, there we go. 5.99 megahertz. I could live with that. And again, the thing to think about is if we're not using the serial chip, we do not have to run at a multiple of a bandwidth. So we can just use whatever we want. We could use 4 if we want. Megahertz, I mean. Now we know we can source the clock for the Z80 using the Atmel chip. Now let's talk about how to use these clocks along with the chip select to read data between the Z80 and the Atmel at a controlled pace.
All right, I have the timing diagram for Z80 I/O access open here in Illustrator, and I've drawn a big red square over it so we can show the passage of time. And then all the signals are on the left. A high-low sequence on the clock is a T cycle. So here's T1. So the clock goes high and then it goes low. That's one cycle. So in the first cycle, the address is asserted. So that's going to be, the I/O device we want to talk to. And down here we see the data is also being asserted. That's if we're writing to the device. Let's look at the next cycle. This one's the key, actually. In T2, your favorite movie, we see that if, read or write is being asserted, it happens after the rising edge of T2. And also, Importantly, IO request goes low, and that's going to be the key later on. It's an automatically inserted wait state that assumes that the IO peripheral is slow, and the peripherals can actually add more wait states to slow down the Z80, which is an option for us, but I have a different solution in mind. So now we're on T3, kind of an underrated movie, I thought. And here we can see on the falling edge of the T3 pulse, IO request and read or write goes high, and then if there is data that is being read from the peripheral, it's going to be sampled on this rising edge. See how the data in is only really necessary there. And then we go back to the next function, another T1. So whatever we do, as far as, controlling the bus, has to be done at the end of the T3 state. So going back to this, T2, I think what we could do is we could use IO request, or at least when it's trying to request the serial device, we could use that to disable the Z80 clock and then use the atmel to manually clock the wait state and T3 so we could have exact control over what we feed back to the Z80 and then go back to the automatic clock to let the Z80 continue processing at full speed. An integrated circuit such as the 6850 serial interface chip, everything in there is a register. It doesn't actually have a program, which means everything happens instantly. So if we're going to interrupt the Z80, we also have to do it instantly, which means we can't do it with code on a microcontroller. We have to do it with gates. And here's what I propose. We have two signals coming into this AND gate. We have atmel serial select, which is active low, and that'll be a address down the road to the multiplexer, but right now we'll just hook it up to the IO request line. So if IO request goes low, that means we're trying to talk to the serial device, right? So as long as this is high, that is not selected, it'll feed a 1 into this AND gate, which means the fast clock, which is sourced from timer 4, that's basically our main frequency of like 6 megahertz, that will be passed through to this OR gate. And the OR gate goes to CPU clock, and I'm going to have an external jumper if you want to source a different clock for the Z80. And then finally it goes to the Z80 itself, right? Well, here's where the magic happens. We have another signal coming from the atmel called slow clock. So either slow clock or the result of this AND gate can feed the main clock. So what will happen is when the Z80 selects the atmel serial, it will also deactivate its own fast clock, because this will go low, which means this AND gate will no longer function, which means we'll get a 0 on the OR over here. But then in our code, we can manually ping the pin for slow clock to advance the T states. Okay, I expanded the timer code to include some tests. I didn't label anything, it's pretty sloppy. Right here we have a main loop. If digital read 7 equals 0, did this go low? So that is the atmel serial chip select, right? So we're basically just using a signal where the Z80 is saying, hey, atmel, I want to talk to you as a serial port, right? So if that goes low, we turn off the fast clock, which is this signal. So this has already been disabled by atmel serial going low, but by turning off fast clock, we ensure that it stays off. And then we jump to access. All right, so let's go to access. Now access, remember we have read and write pins connected between the atmel and the Z80. So access is just going to see if this is a read or a write function, and then it's going to return data differently based off what function it is. Let's just say it's a write function for now, okay? So if it's a write function, let's bring up this again. All right, so as we talked about over here, the data should already be present at the end of the T1 cycle. All right, so let's go back over to the illustrator thing. So we're right here, basically. So the T2 function, even though we have chopped it off short, it's only the rising edge that matters. So we're right here in the T2 function. So the data for a write should be valid, and also the write signal strobe should be low. Serial write byte in. So what we're doing is we are reading what's on the bus, which is byte in. We're reading what's been put onto the bus, and we're sending it over our serial port. Really easy. So we do that immediately. Now I'm using digital writes here, which are slow, but again, it's just an example. So we need to get through the states. So we're going to go through the wait state. So over here on the right, okay, high, low, that's the wait state. And now the T3 state. Okay. Now this is important to note. See how IO request is deselected in the state? So if we hadn't have turned off the fast clock, which is this signal here, then the Z80 would immediately fire up again and we lose control. And the reason that's important is because we have to make sure that we release our data bus, at least if we're writing data, right? Because the data bus of the Atmel is connected to the data bus of the Z80. So we have to make sure that the Atmel bus is in tri-state so it doesn't affect anything else on the bus. That only occurs in a read cycle, but we can look at that next. All right, so once we've done that, once we've cycled manually through the T states, then we reactivate the clock, which is the next T1 cycle, and then the Z80 is off to the races. So the Z80 is only slowed down while it's accessing us as a serial port. By us, I mean the Atmel processor. All right, let's take a look at the read function. It's pretty much the same. So this is the Z80 reading the Atmel. So the data out function, that is the Atmel processor making its bus output so the Z80 can read it. Byte out, that is the Atmel asserting the data on that port. Even though the Z80 isn't going to read it yet, we're just doing it right there so it's ready. Okay, so now we advance the wait state. Then we advance the T3 state. And this part's a little different. So we're going to go data high Z. So what data high Z does is it basically turns the Atmel's bus back into inputs so it won't affect anything else in the computer. And that's why it's important to actually clock through the T3 state manually, because if you look over here in the timing diagram, in the next state, our bus has to be released, right? By doing our high-low pulse here on T3, then we can hold the processor right here, release the bus so we're no longer affecting anything, and then let the Z80 continue its work. So yes, by being able to control the clock pulses during an I/O read, we can ensure that the data is correct. We can make sure that the Atmel can provide the data in a timely fashion, which it wouldn't be able to just using code unless it was much, much faster, probably like at least 80 megahertz. And we can also make sure we don't affect the bus negatively. So that's the theory. Let's test it out. Oh my gosh, clock cycles, T states, registers. How much geekier could this get? Haha, hold my spotted cow. Here is the source code that is on Grant Searle's site for his example. Is it Searle or Surly? It can't be Surly because that sounds like, like, oh man, that's a surly looking mate. Anyway, he's got the source code, and guess what? It's in assembly. Dun dun dun. There's two parts to it. There's an initializer and serial interpreter, and then Microsoft Basic itself. So let's just look at the serial interpreter. So this is going to set origin of 0000, which is where the Z80 vectors to on reset, aka its reset vector. And then he's got some other pointers here for transmit and receive. The main thing we're interested in is the in and out port. So in A80 means that the Z80 is loading the contents of IO device 80 hex into its accumulator. And then 81 is also one of the registers. So there's basically two registers on that serial chip, and whether you read them or write them, you get different results, right? Register 80 is a configuration register, but we don't really need that because we don't need to configure our chip because we're pre-configuring it. So all we need to think about are the examples of in 81 and out 81. So let's just take a look at the code here and change everything. All right, so we're going to look at the status register of the chip. So the chip basically creates an interrupt when it receives a character, and then the Z80 jumps here. It pops its accumulator onto the stack. So it's going to check and see if the interrupt is due to the receive register being full. If not, it ignores it. Okay, so we don't need to do that because that's the only reason we would interrupt the Z80. Okay, so in A81, that's going to be the Z80 reading the character that the Atmel has made available. And it's going to put that onto the stack and check it's, okay, we don't need to worry about that. Blah, 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 blah. Okay, then like down here, it looks like it's resetting that device for the next thing to happen. Let's see, jar, RTS full, jump routine. So I believe we can get rid of that. Hey, this will also save us time because we're not sitting there doing checks. We're basically just doing the data. All right. Okay, this is also sending something to the control register. Don't need that. Okay. Oh, this is where it's sending a character, transmit. It's putting the character that it wants to send on the stack, Oh, the stack is a temporary area in RAM to put variables that you can't fit into the meager registers of the CPU. Then it's getting the status byte from the serial chip and comparing it. So we actually don't need to do any of this because the Arduino is fast. It'll always be ready. So basically, we're going to get rid of all that stuff, which will save us time. And we're also going to get rid of the stack access, which is good. We're just going to immediately output the character onto the bus. And let's see. Okay, here's initialization of that. We don't need that either. So we'll get rid of that and the associated load accumulator. Okay, that should be it. All right, I'm going to save a copy of this. And now we have to compile it. Oh, look, he included TASM, the compiler. Let's try to run it. Oh, no, we can't run it. That's right, it's time for DOSBox. Let's see, mount C as C. What is that, TASM? There we go. Okay, so I've DOSBoxed into this folder. Okay, so TASM for the Z80, FFF flags. We're going to make a binary file, not hex, and we're going to do int mega, which is my new version, ASM, and our output's going to be int mega binary. And there we go. And we can take a look at it with our hex editor. Well, you can see there is some text in it, some ASCII readable text like cold or warm start, and grant Searle, not surly. But wait, there's more. So yes. So if we go into the basic assembly listing, org 150 hex. So that's where basic's going to start in memory. Now you might be like, why is that important? Well, it's like, because we have to create a binary file. There's probably better ways to do this, but I don't know. So I'm just going to do it manually. So I'm going to take the int mega that we just compiled. I'm going to put it in here. And I'm going to make sure that I'm just going to put a bunch of F's in so we get up to 150. All right, there we go. So we don't want the F's there. Then take a binary version of basic, select all, copy, go back into int mega. Okay. Now we have a binary file that we can write to an EEPROM. Now I know that we were using RAM loading programs before, but just to make this as surefire as possible, I'm going to burn this to an EEPROM and test it with one of my older Z80 boards, just so we know that all is working. All we'll be testing is the serial port access.
Okay, I use my Batronics programmer, it's very nice, to program a new EEPROM. I've got it in my system. I have the Arduino all wired up in parallel. The serial chip has been removed. I do have the enable line here. We can use that on the scope to compare the clocks to when the Arduino is being accessed, but everything should work. So I'm just going to load up that code I showed you earlier that has, you know, the port access stuff in it, and then we'll try it out in PuTTY.
Okay, like before, I've connected to the Arduino using PuTTY. I'm going to tap reset because this board doesn't have a controlled reset. There's our message. Cool. Memory top. All right. And if we do a reset, it'll ask us if it's a cold or warm start. Like before, cold, erase memory. Cool. All right, now let's look at what's happening on the oscilloscope when we do that. Okay, so if I type a character, you should see some glitches, right? So what we can do, let's see, so we can set up a trigger. So I've got the enable line from an old project hooked up. So if I go trigger type, I'm going to go source to, slope rising, and voltage there. So if I, okay, that should be it. So if I set it to single, we should be able to capture the port access. Yep, there we go. All right, so this line here indicates the Z80 trying to talk to the port. And this gap here, that is the Atmel preparing the data that the Z80 has requested. And then here, you can see our two manual clock pulses from the Atmel device, basically, you know, giving the Z80 the data it requested. And then here you can see the Z80's fast clock resuming. So it is a huge difference in clock speeds. Now, again, we can try to speed this up, but again, this is only going to happen when characters are being sent. So like right here, for instance, that's me sending carriage return new line by pressing return. That's me sending it. And then remember, it's having to make things show up in the terminal. So right there, that is the Z80 sending back what I just typed so that on my PuTTY screen, we see the cursor move. All right, print, of course, hello world, 19, go to 10. See how that looks on the scope. All right, so here you can see this is all of the processing from the go-to basically, and there's the print. Remember, basic is slow. But the print statement, well, here, let's make this a little simpler. Go back over here, list, print, ABC. Well, it'll ABC plus carriage return new line, so it should be 5 characters. So we should, yep, at 5 gaps there. Well, I'll optimize the code to make this gap as short as possible. And also remember, I was using digital write, which is kind of slow. Actually, we can see if we can speed that up. Let's see, what do we got? This is, how long is this? It looks like it's approximately 1 eternity. It's about 6 microseconds. All right, so let's see if we can beat 6 microseconds. All right, let's try to speed this up. Digital write 3 is our slow clock at the moment. So where's pin 3? There we go. D3, which is PD0. All right, so we will do this. PD0, port D or equals 1. That will set that high. Port D and equals FE, that will set that low, and without affecting the other bits. Do that twice. Also do it down here for read. Let's send it and see if there's a difference. Let's do the same thing as before. Print ABC, that's how easy it's going to be. Go to 10, run. All right, let's get it on the scope. Look how much faster that is. You can barely even see it. Wow. Okay, so that just goes to show you, that's even more severe than I thought it would be. That goes to show you how slow a digital write is, because look how much faster it got. We went from like 5 microseconds to about 200 nanoseconds. I wonder if we can optimize anything over here. If digital read N7. Oh, no, another digital read. Evil, evil. Okay, let's see. So that's D7, which is PE6. All right, let's go back to our code. PE6. So that's if pin E and 6. So we can just write that as 1 bit shift 6. The compiler would take care of us. If pin E and 6. Okay, then we can go a little bit more. We can go not. So basically, we're going to AND the port pin E, which is the input side, with a bit mask to the 6th bit. And if it does not return true, then we'll execute the statement. Oh, I love this stuff. I love optimization, throwing things away, not cleaning so much. Oh no, look, we're using a digital write to do the IRQ. Oh, so evil. Let's see, digital write 4. That's D4, PD4. Port D or equals, we can also do 1 bitwise 4 to the left. You don't have to worry about that costing time because the compiler will just automatically, create that value for you. Same thing here. We can do port E and equals the inverse of 1 bit shift 4 to the left. Oh wait, but in this case, we just want it to go low. Yeah, we're not pulsing it, we're just pulling the IRQ low. Good thing I caught that. Otherwise, we would have been up a creek. Then down here, it will just replace the other digital write 4 with that. So we're going to release IRQ. Clock on, clock off. We're doing direct register access, so we don't have to worry about that. Byte out. This is all direct register access. Data high Z, we could probably speed this up, but that's not as important. Let's see if there's any more evil digital. I don't think we're even using this function, so goodbye. There is another one. Oh yeah, we're checking to see if it's a read or write. Digital read 2. All right, so that's, there's 2, PD1. All right, let's replace this. If pin D and, what would that be? 2, second bit. Okay. Find all instances of digital and wipe them out. All of them. Okay, it's only happening in the setup now. Good, as I have foreseen it.
All right, let's see how we're doing now. Not a huge savings there, although we're still doing better. Something else we could do, I think we are actually loading the Arduino serial buffer as soon as we get the data. We could wait until after the transaction. That way the Z80 isn't waiting for us to do that.
We'll just do char, I don't know, Rx equals byte in. So we'll grab what's on the bus right away, right? Then we'll do the port stuff. Then we'll allow the Z80 to continue. And then after that, then we'll send the byte that we got. Because remember, there's a lot of stuff happening under the hood with the Arduino core. You know, like there's buffers and timers and stuff. So let's not do any of that until after we've let the Z80 go along its merry way. So yeah, we're going to get the byte immediately, do the clocks, resume the Z80 fast clock, and then write what we got over our USB port. Let's try it out.
Okay, running the same example again. We are looking at about 3.3 microseconds. That's a win! So yeah, we took out all the digital writes and reads, which sped that up immensely. Then we moved the expensive serial write buffer command to after the Z80 access. We can probably even get this window even smaller, but it's in the grand scheme of things, look how much smaller it's gotten. Isn't that great? So even though this is a relatively slow MCU, by optimizing a few things, we can get pretty decent performance out of it and impact the Z80 clock as little as possible. Winner, winner, chicken dinner. I cut my thumb doing cabinetry work.
Now that I know I can remove that large through-hole obsolete serial chip, I can fine-tune my PCB design. So let's talk about what I have so far. All right, so here's what the front of the board looks like. Now this is going to be pretty small. It's actually smaller than a Post-it note. Take a look at this paper printout, right? It might seem a little too small actually, but again, I want to make this thing affordable. So the smaller the PCB, the cheaper it is. It's actually one of the major cost factors. All right, let's take a look. Right here, we have the Z80 itself, surface mount. Right next to it, we have a 138 3 to 8 multiplexer demultiplexer, which we'll use to select logic, such as telling the Atmel chip that we want to select it as a serial device. And then also I have most of the chip select stuff going to the card edge connector if you wanted to attach like an external video chip or keyboard. Over here we have the two 32K SRAMs. It would have looked cooler to have them flanking the CPU, but from a design standpoint, it's better to have them right next to each other. Right here we have a transceiver bus. So this allows the Z80 to talk to the switches. I have like a little mini joystick here. It allows it to talk to the switches, and we can also map those switches to the Atmel. So either the Atmel or the Z80 can read the face buttons, and they won't interfere with each other. Over here we have the NAND and the OR gate. I have simplified this a little bit. I think I can get away with just two of these, so a quad NAND and a quad OR. Power switch is going to be over here. That's probably going to change a little bit. Like B and A buttons, you know, like a joystick. Up here at the top, well, we have the slits for the lanyard clips, but also right above that, I'm going to have exposed pads. So this would be a convenient place to clip on alligator leads if you want to do some testing. USB port. To make it easier to solder, I'm using a resistor array through hole for most of the buttons. Yeah, so pretty much everything in the front of the unit is Z80 related. And then the back is where I have the cheater chips, so to speak, right? So on the back of it, we have our surface mount ATmega 32U4 right there. I've switched out the shift registers. I'm now using IO expanders. The reason for that was a lot of people asked for a SD card reader. That tends to hog the SPI bus in the Arduino software. So instead of using SPI shift registers, I'm now using I2C IO expanders. So they're a little bit more expensive, but it'll be more convenient in the end. So there's 3 of them. There's 2 to change the address bus, which we talked about in the first video, and the third one is what the Atmel uses to read the switches and buttons, right? All of the surface mount resistors are on the back of the unit just to make it consistent, and I'm also trying to do it with only 1K and 10K resistors, so it's not too confusing for people. Then here's a jumper if you want to have an external clock. I should also attach the external clock lines to one of these pins down here. I bumped this up to a 50 pin connector, which is actually the same as the Sega Master System. And then I don't want to make people solder a surface mount crystal. I think that is a bit much. So I've just got a through hole standard crystal there. So my next steps are to order some parts just to make sure that the IO expanders are going to work. And then once I know all those things work, I will order some test PCBs and start working on the code, basically taking all my example code and merging it together into one big program. I'm also going to be using one of these SSD 1306 OLED modules. This particular one is in SPI mode. I've ordered some I2C versions. Again, you know, I2C, you can put, what is it, 128 devices on a bus? Well, theoretically. So basically, I can put these on the same address bus as the IO expanders and save myself some IO and also fewer external processing chips. Because again, as I said, I want this to be like a 3 to 4 hour max session. So I want to make sure that everyone can finish their board in time and take home a cool single board computer. Yeah, I'm going to have a module for a SD card reader on the back, such as this one right here. These are really cheap on Amazon. And I thought about adding a I2C EEPROM. I still might do that, or it could be an option. As you may notice that there's no battery backup. A 2032 coin cell is quite enormous on this board. And I figured if you have an EEPROM and a SD card, there's really no need for battery backup because you could basically do a RAM dump to solid state flash and load it when you boot back up. And again, we can have like a little menu on the screen, on the OLED screen. So when you boot up, you can say, oh, I want to do this. I want to load this image or this file, blah, blah, blah. And then it'll load it into the Z80's memory. And then you could also use it to do a RAM dump. Of course, the big reason to have a screen is so when you wear this as a badge, people can see it doing something. All right, well, I think that's enough for this installment. I'll probably do another installment once I have the test boards in. So that will probably be about 2 weeks from now. So I guess stay tuned and fingers crossed I can get this done in time for Midwest Gaming Classic, which is beginning of April. All right, we'll see you in the next video.